So good afternoon again, everybody. My name is Cameron Yunus. I'm a member of staff here at the Department of Chemical Engineering and Biotechnology at the University of Cambridge. And I'm welcome to the presentations from our finalists on the Davidson Inventors Challenge that we've been running throughout the last few months here at the department. So all I'm going to be doing just shortly is just go through what's going to be happening in today's webinar. So the first thing I'd like to point out is some housekeepings. Please note that this event will be recorded. You will notice that there are a number of panelists on this call. They all have their mics and video feeds off, but as we go through the webinar, I will be introducing some of these panelists who will then come onto the call to give short talks or presentations. The other thing to notice is that this is a Zoom webinar. And on the Zoom webinar, you will notice that there is a tool, there is a bar that should appear at the bottom of your screens. And one of those icons on the screen should say Q&A. And I would encourage all participants and all panelists to use the Q&A feature throughout the call. So what we're going to be having is 4 of our finalist teams presenting today. And after their short presentations, there will be an opportunity for some Q&As. If you post any questions you have on using the Q&A feature, I can then direct those questions to the panelists during their question and answer sessions. And just for safeguarding reasons, I just wanted to point out that for the camera and mic feature for all participants is turned off. And if there are any concerns about any safeguarding or moderation, please do note our safeguarding officer in the department is Alana Gonzalez, and her contact details here below. So just to kind of introduce what this is all about. So the Department of Chemical Engineering and Biotechnology here has been in the West Cambridge site for a few years. We're a fantastic new building here at the West Cambridge site. And over the last 2 or 3 years, we've been very focused on seeing how we can engage school children, kids, young adults in school to think about chemical engineering and biotechnology as a discipline to study at higher education. So the whole idea behind this competition is really to try and engage schools and students which are going in through their GCSEs and A-levels to think about this discipline and really try and understand, get some context behind how broad the discipline is. So the competition is all about looking at the Sustainable Development Goals, which has been set by the United Nations, and seeing how these global challenges some of these global challenges can be addressed through the discipline of chemical engineering and biotechnology. So really trying to show how the discipline is very diverse and has applications in a diverse range of issues which we are facing today as a society, as a civilization, and as we move forward, and how we want to build the planet as we move forward to be more sustainable, healthy, and environmentally friendly and for a place to live. So today's webinar, what we're going to be doing, I'm here giving just a quick intro into the webinar. I will be passing on to the Professor Clemens Kaminski, who's the head of department at the department here in Chemical Engineering and Biotechnology. We'll be giving a short overview about the department. We will then move on and start the presentations. We will have our 4 finalists presenting their work to us. And between each presentations, there will be a short Q&A where I can then present them with any questions that have been posted on the Q&A feature. Once the talks are finished, there will be a 10-minute pause. Please don't leave the Zoom call, stay on the Zoom call. There's just be an opportunity for everyone to stretch their legs and grab a cup of tea. And during those 10 minutes, the judging panel will be deliberating to choose who will be the winner out of our 4 finalists. And then at 4:30, we have Dame Judith Hackitt, who will be giving a short talk about her career and how she's gone on in her career and the things she's been doing, and really talking about how she started off her career as a chemical engineer. And then at the end of this, we will then hopefully be able to pass back on to Jane Cutler, who is the president of the Institute of Chemical Engineering. We'll tell you a little bit about the IChemE, and we'll then hopefully announce who our winner is out of our 4 finalists. And hopefully the plan is to kind of wrap up and finish this webinar by 5 p.m. today. So just before I pass on to Professor Kaminsky, I just thought it'd be really important to just highlight some of the key players involved in helping us set up this competition. We've worked very closely with ASTI, which is an organization in Malaysia, which do a lot of outreach events with schools and students, young adults in schools to engage them into science and technology. So a big thank you to Dr. Yunus Yassin, who heads up ASTI and who's been very pioneering in help us develop this competition. We'd also like to point out that we've had a lot of support from the ICME, so a big thank you to them, and all of our participating students who have made this such a successful competition, and all of the support from the reviewers and mentors who've been helping us out throughout this time. And last but not least, I'd like to welcome our guests, Dame Judith Hackitt and Jane Cutler, who've taken time out to join us today in celebrating this competition and hearing from our 4 finalists. So without any further ado, I'd like to pass on to Clemens, who will be giving you a short introduction into the department.
Well, thank you very much, Cam. Can you hear me okay? Yes, okay. So a very warm welcome to this fantastic event today. It's one of the most exciting things we do, getting young, bright minds like yourselves to think about problems that have a global dimensions, global challenges. This is pretty much what we do in our department as a whole. My colleagues are absolutely brilliant at taking fundamental science, understanding things at the smallest level, all the way up to big systems. So we're not just physicists and chemists, although we are that too. We look at, what a molecule might do when it interacts with light. We might be interested in seeing how that molecule turns that light into electrons that can be used to drive currents and generate electricity. But it's not just that. Our researchers, they look at how to make large panels where you can paint these molecules. You can paint these molecules onto so that you can collect the light, the sunlight, and turn it into electricity on panels that you can put on your houses or maybe even as small sheets on the windows. So our researchers have a curiosity to try and understand what goes on in nature. But not only that, they are keenly focused on turning their knowledge into processes, into systems, into materials that benefit society. We do this in 2 themes where we think we really make world-leading impact. One is in healthcare. So we are keen to drive technologies that benefit people in any in any country, anywhere and everywhere, by making healthcare solutions that are affordable, that can be scaled, so they serve masses everywhere, and so they become affordable as products and as diagnostics and as therapies. We also have an impact theme in sustainable processes and technologies. So these are energy conversion technologies, new ways of making chemicals that replace polluting processes or polluting chemicals that are made from fossil fuels and so on. We are driving materials research to make energy conversion processes possible, as I just mentioned earlier on, that help us drive the fossil fuel transition that we so desperately need to make progress with. So that's what chemical engineers do. They have a curiosity in understanding fundamental principles, molecular level processes, and take these processes and make and develop technologies that benefit society. And in a way, that's what you have been doing with your projects too. So many congratulations on getting so far. The 4 teams that are presenting today, good luck to you all. You've done a fantastic and very challenging project each. And I'm really looking forward to your presentations. I wish you very good luck. I hope that you'll be interested in joining us. You are, of course, going to be the next generation facing the challenges that we have now with new processes, with new technologies, with new ideas. So I encourage you to look at the discipline and encourage you to look at our department, to look at what the people do, look at the news pages. It's full of things that show you the impact that the people in our department are making. If you want to join, what you need is a solid understanding of basic sciences, fundamental sciences of physics and chemistry. You will learn that. You will also need to be good at math. We need to understand these processes and then actually use math to try and work out how we can scale up processes and not just understand the process, but actually make them at scale. So math is a big thing in our discipline. So you need to be curious about that. But the final thing that you need to bring is curiosity. That's really the most important thing, and really a willingness to think beyond the outside of the box. Really, that's what's key. I mean, you know, you've already shown that you're capable of doing that. So that's absolutely essential. Our students and graduates and our researchers, they are system thinkers. They think really big. They think from the smallest to the largest scale, and that makes them highly valuable to society. They are valuable in many domains that can range from the chemical industries to the biological industries to the healthcare sector to the financial sector. They're highly sought after. On average, the graduates from our discipline will start with some of the highest salaries that of any discipline, and so they are highly sought after, very versatile people, just like yourselves. So I'm not going to hold this very important event up any longer. I am really looking forward to this, and I'm passing back to Cam. But before that, let me also thank Judith and Jane for making time. These are some very important people you're going to meet today. They are supporting this event, and I'm thanking them, and of course, all the sponsors that made this possible. So good luck and have an enjoyable day. And please do stay in touch and get in touch if you have any questions.
Many thanks, Clemens. Okay, so without any further waiting, let's move on to our first presenter. So we're going to be hearing from our first team, which is called Izzy Solution. So I'm going to hand over to Izzy Solution to share their presentation and make a start.
Could I just test? Could you guys hear us?
Yes, we can hear you, and I can see your slides.
Perfect. That's brilliant. All right. So hello, everyone. We are Izzy Solution from Eastbourne College. We are delighted to have the opportunity to present to you our invention of the solar water sterilization system. The problem we would like to address is the lack of accessibility to potable water for people worldwide. Inaccessibility may lead to severe physical and mental problems for human health. In total, poor water quality leads to 1.2 million deaths per year. Our case study focuses on the Democratic Republic of Congo, or the DRC. Although the DRC has abundance of freshwater resources, 33 million people still lack access to clean drinking water. This is because public water facilities and networks in the DRC are inadequate to sterilize and deliver the water. In the Second Congo War, many important infrastructures collapsed. The basic water facilities are available to only 52% of the DRC's population, and less than 29% have access to basic sanitation. Secondary consequences also include more hospital beds taken up and the removal of able workers from the workforce due to waterborne diseases. Lastly, the burden of fetching water usually falls on the shoulders of young women. Fetching water is time-consuming, preventing women from receiving education or working, which also contributes to gender inequality. Instead of multilateral or bilateral aid, we believe Izzy Solution, a bottom-up solution, will be more effective. In 2015 September, the UN adopted the 2030 Agenda for Sustainable Development that includes 17 Sustainable Development Goals. Our project focuses on achieving the 6th SDG, which is to ensure the security of potable water and basic sanitation for all. However, as suggested, our prototype can ensure the progress towards other SDGs as well.
The simplest yet most effective solution is by boiling water, which causes pathogens. The source of the energy to do this is from electricity, generated either by fossil fuels or less commonly renewable energy. However, 940 million people do not have access to electricity, so boiling water is done by combusting wood. Some major drawbacks include the emission of pollutants, high cost, and not to mention, it is unsustainable. Less conventional methods include the usage of UV light, chlorination, and reverse osmosis. Despite effective methods of UV light and reverse osmosis are significantly more expensive and requires a high level of technology. Chlorination tablets also have a very short shelf life. While heating water is the most common method, we realized that there are many means to heat the water without direct boiling. As a result, we decided to use solar energy as the foundation of our approach.
Now we will move on to the plan of our solution. We planned our solution by considering the following aspects. First is the energy source. We need to use renewable energy and maximize energy accumulation. Next, we need to decide how we are going to use the energy. To reduce the energy cost, we should make energy transformation as direct as possible. Moving on, we need to increase the conservation of energy. This involves finding absorptive, conductive, and insulating materials. This is the model we designed. We decided to use solar energy as our energy source. As the lens collects the light rays, the thermal energy at the point of focus is increased by A over A, where the capital A is the area of the lens and small a is the exposing area of the metal. Radiation is then absorbed by highly absorptive material, such as carbon dioxide, and is conducted directly to the water. The insulation layer consists of radiation reflective silver covering and conduction resistive vacuum. The shape of the container is designed to be spherical to decrease the amount of radiation from the surface. Unfortunately, we are unable to build an actual prototype of our design due to inaccessible manufacturing processes. However, we managed to build a simpler version of the prototype using waste material. Tube 1 is the control group, which is exposed in the sun. Temperatures of both tubes were measured every 10 minutes. As shown in the graph, the energy absorbed by the water with conduction and insulation is 3 times the one without. Though the absorptivity of solar energy is only 4%, there is an overall temperature increase of 88.6%, showing a positive effect. We also built a mathematical model of radiation at the surface of the exposed metal using data of carbon dioxide. Due to the low surface area, energy emitted is less than 0.1 joules per second. This shows that most of the energy is conserved.
Moving to a local scale, a structured and magnified system is required. As illustrated in the diagram, the system consists of several boiling and insulation units with lens adjusters. Water is first filtered by a ceramic filter, then stored in the column on the right before it is redirected into the heating unit for further sterilization. Once the temperature rises to a certain value, the auto water controlling system opens the water gate. Unsterilized water replaces the disinfected water, while the latter goes into the water collection tank, ready to be used. It is important to customize our product into different scales to suit the needs of each specific area. This is a mathematical model we can use in the manufacturing process, where the size of lens and the mass of water produced per day can be adjusted. The estimated cost of 100 cell system is around £4,000. Using the average daily solar hour of the DRC, a large-scale system can produce 2,018 liters of clean water per day. This means we can provide enough water for 1,009 people, and the average cost is lowered to £4 per capita, with no future consistent purchases required for the heating part.
Moving on to evaluation, we would like to relate our system to the 5 Ps. With sanitized water, the health of people in poor rural areas can be improved. Our system does not produce greenhouse gases when used, and is produced from recyclable materials, which helps contribute to the objective of planet. Our system is relatively low cost in the long term. This can lower the proportion of income used to sanitize water, as well as the medical fees required to cure diseases related. This relates to the objective of prosperity. In conclusion, we are satisfied by the progress made. Not only did we investigate real-life examples of the problem, we also came up with an innovative solution and a detailed plan, backed up by the creation of several models. In the future, after we have done the further testing needed, we would like to contact manufacturers to produce a prototype. To begin with, we would start by testing the heating unit and the ceramic filter, then the whole system to make further adjustments. Our final goal is to contact local government to implement our system. Turning next to future applications, we hope to construct a piping system to ease the fetch of water. Moreover, we can modify our system to heat up other materials, such as metals. If we can circulate water between heating units and the target object, we can achieve constant temperature for agricultural production, biological engineering, etc. Here are the references. This concludes our presentation. May we now move on to the Q&A session.
Sorry, I was on mute there for a minute. Sorry, I didn't realize. Thank you so much for your presentation. I have some questions which are coming up. I have one from Judith Hackitt here. Question is, given you managed to get beyond, you haven't managed to get beyond lab scale testing, what would your proposal be for the next stage of scale up before going for funding and onto commercialization? So you've done something on the lab. What do you think will be your next stage in your sort of scale up process?
Well, I think it is really important that we have our a very similar prototype manufactured, because the core concept of our system is that the insulation part is the conservation of energy, and only when the conservation of energy is ensured that can the temperature raise up. So I think we'll just, firstly, we need to do a small scale of the system, and then we'll test it in our lab. And then if the temperature has already gone to the value we expected, then we can move on to the further testing of the whole system.
Okay. All right. Another question's come up. How does the system deal with the changing position of the sun in the sky? Do you need to include moving parts, and does that make it more expensive and complex?
Yeah, we have thought about that. We have included in our adjusters of the lens. It includes 2 parts. The adjuster has a weight support, which will support the lens and make sure it's located on top. And also it can ensure that the distance between the lens and the metal is fixed all the time, wherever you move. So the focus lens is ensured. And then the other part is that we would like to set up a circuit powered by a tiny solar panel. And that circuit will involve thermistor. And actually that will involve light-dependent resistor, which will locate around the metal. So when the focus point move, which means that the sun has moved, then the circuit will detect it and then do the corresponding adjustment.
Yeah. Okay. Another question. What sort of temperature do you think your device will go to? And thinking about temperature, how do you think your system will handle viruses?
Well, because our end temperature is around 100 degrees, but I think it is actually it is the time which matters. If it can keep above 80 degrees for 10 minutes or 20 minutes, that means that most of the bacteria will be killed. For the viruses, because our system is only an alternative way to the other systems, because so that energy used is more sustainable, and so it is more environmentally friendly.
For the viruses part, by high temperature, viruses have enzymes, and with high temperature, the enzymes in the virus deactivate. So this is how we hope to eliminate the viruses. And for bacteria, most of the bacteria is actually killed by high temperature, and only a few can survive the high temperature.
So the other thing, one last question then, because we need to move on to the next team after this. How is the water stored after treatment to avoid it getting contaminated again or growing bugs?
There is a column in the right, and it won't have any contact with the outside environment, so it will avoid contamination.
Okay, great. Thank you very much, Izzy Solutions. Thank you so much for your presentation. We'll now move on to the next team, which is Falakas. So over to you, Falakas, for your presentation.
Yes. Is that sharing?
I can see your slides. Yeah.
Okay. Right. Good afternoon. We are Team Falakas, and we're going to be discussing our project, the goal of which was to synthesize a reinforced starch screen protector for a smartwatch. So let's start with some background to the problem. As global GDP and level of development have risen, so too has the global demand for goods. And these goods have to be made from materials. So we can also say that the global materials footprint has risen greatly. One of the most prominent materials produced is plastic, and most of this plastic is produced using petroleum-derived feedstocks or raw materials. And this can negatively impact the environment, ranging from greenhouse gas emissions to ecosystem pollution and destabilization. So one alternative to this is bioplastic, which is sourced using plant-based feedstocks instead. This avoids the negative impacts of petroleum-based plastics. However, the adoption of bioplastic has been quite limited so far, and there are multiple reasons for this, such as cost, supply chain disruption. However, the reason we're going to be focusing on is inferior mechanical properties. That is to say, that bioplastics can be weaker than their petroleum-derived counterparts, and this is usually due to fewer crosslinks between the bioplastic monomers.
This gives rise to our thesis that the mechanical properties of starch bioplastics must be improved. In addition to technical benefits, there are also social and economic benefits to answering this question. Notably, the United Nations Sustainable Development Goal 12 would be fulfilled, and if bioplastics were to be widely adopted, so too would sub-goal 12.7 to promote sustainable public procurement practices. The 5 Ps that underpin the Sustainable Development Goals also have a part to play, as the replacement of petroleum feedstocks with agricultural ones means that farmers in low-income countries can collaborate with multinational corporations to create a bioplastic supply chain. This, in turn, opens new revenue streams that can be used to fund development.
As mentioned at the start, this project aims to make a reinforced starch screen protector for a smartwatch. Let us briefly talk about why we chose this application. Firstly, a screen protector is relatively easy to synthesize from a bioplastic sheet. All we need is a template, which can be used to cut out the desired shape. Secondly, a screen protector is a relatively low impact product. That is to say that it isn't being stressed continuously. It would be rather difficult to make a bioplastic strong enough to replace PVC pipes, as PVC is the perfect material for absorbing the stress from constant high pressure fluid flow. However, it is possible to make reinforced bioplastics that can withstand scratches and smaller impacts. We focused on smartwatches as this is a technology sector that is experiencing rapid growth as more and more people buy smartwatches every year. We also reasoned smartwatches would be a stepping stone to other items such as phones and laptops. This is because the cheapest smartwatches are around £40, whereas the cheapest phones are much more expensive. Therefore, some would be more inclined to take a chance on a new screen protector for a cheaper smartwatch than a phone. After seeing the success on the screen protector, they would be more inclined to buy it for a phone or laptop. On the screen is a skip with around 60,000 old phone screen protectors and cases. This would usually be sent to landfill. Therefore, if we replace this with bioplastic, we could potentially go a long way towards reducing plastic pollution. Additionally, there were some requirements that the products would have to meet. Transparency to enable the screen to be seen, low thickness to allow for touchscreen features, as well as durability and affordability, as any bioplastic product would have to be competitive with existing products on the market.
Keeping all this in mind, we set to work and met weekly recording our progress on OneNote. Starches from 4 staple crops were used as feedstocks. These were cornstarch, potato starch, sweet potato starch, and rice starch. In addition, vinegar was used to break up the starch polymer chains to reduce brittleness, and glycerol was used as a plasticizer to provide lubrication within the bioplastic by absorbing water and increasing pliability. Alumina was used as a hardener. The raw materials were mixed for 3 minutes, then the mixture was heated on a medium Bunsen flame for 4 minutes. After leaving to cool for 5 minutes, the mixture was left to set for 8 days on aluminium foil, as well as thin sheet samples. Slightly thicker samples for strength testing were made in weighing boats. The samples were tested to see how much mass they could support before tearing. This was done by inserting a small metal rod at the top of the sample and a mass carrier at the bottom. The mass was gradually increased by 100 grams, then 50 grams after the yield point. The yield point in this test was taken to be the mass at which the samples began irreversibly deforming, and the breaking point was the highest mass the samples could support before completely breaking.
Before looking at the results, we would like to discuss the role of the aluminium hardener. Many metal oxides, for example, zinc oxide or titanium oxide, can be used as hardeners to prevent the polymer chains in the bioplastics from sliding over each other as easily. However, aluminium oxide has the capability of producing transparent matrices when mixed into bioplastics. This makes it the ideal hardener for making a screen protector for a smartwatch. As the map shows, alumina is also very widely produced. This means that if this screen protector was put into production, sourcing the raw materials would not be a great challenge. Moving to the results. In general, alumina reinforcement was successful in all the bioplastics, as all the bioplastics were able to support a greater mass before breaking. The sweet potato with alumina bioplastic produced the best material for a screen protector, as the rice with alumina was far too opaque and the corn and potato with alumina were too adhesive and difficult to remove from the foil. In addition to this, they were far too thick, preventing touchscreen features. The sweet potato with alumina bioplastic was adhesive on the foil facing side due to less water evaporating on the foil facing side as opposed to more water evaporating on the air facing side. This helped to place it onto the smartwatch surface. When removed, the screen protector left no residue on the screen. The product stood up to scratch testing using a spatula, needle, and fingernails, necessary for any smartwatch screen protector. It's also had a reasonable cost of 33 pence, so the product fulfilled all the goals that were set out at the start.
In addition to the successes of the project, it's also important to evaluate possible areas of improvement and to discuss future developments. One major improvement would be the eradication of air bubbles in the bioplastic sheets. Air bubbles reduce the transparency of the screen protector, and one way to eradicate them would be to blow warm air over the setting sheet. There was also some shrinkage of the bioplastic sheet as water within the sheet evaporated away during the drying process. This was an unforeseen event, and so a solution would be to have a larger sheet with some recyclable excess that could be trimmed off if required. As mentioned before, some of the bioplastic samples were difficult to remove from the foil, and so this could be remedied by using a different setting surface, such as parchment paper or cling film. Looking to future developments, the volumes of glycerol and vinegar could also be modified to find an optimal combination for good rigidity and pliability. The starch could be dissolved away using acid and heat, so the alumina hardener could potentially be reused through filtration and centrifugation. Finally, another point to address is the use of arable land for bioplastic production. Whilst this was a concern at the outset, further research showed that even if we would base all the present worldwide fossil plastics production on biomass as feedstock instead, the demand for the feedstock would be around 5% of the total amount of biomass produced and harvested per annum. This means that even if bioplastic demand increased by a large margin, there would still be minimal stress to the food supply. It must also be ensured that food wastage is minimized to avoid straining the food supply chain any further. So to conclude, this project achieved the stated goal of synthesizing a reinforced starch bioplastic screen protector. The screen protector used starch from staple crops as a feedstock and was relevant to the 5 Ps and United Nations Sustainable Development Goals. Finally, the successes and points of improvement were also considered. Overall, the project was successfully concluded. Thank you for your time, and we welcome any questions. Thank you.
Many thanks, Falakas, for your presentation. We have some questions posted here. One of the questions you've tried to address in one of your slides, which is about how it competes with arable land for food feedstocks. But can you talk a little bit more about the moral, ethical issues associated with using foodstuff to make bioplastics rather than feeding people? Do you feel that this is still going to be something that you will need to tackle if this was to be implemented?
I think that with regard of feeding people and the lack of food, we must also consider the distribution of food, because there's great inefficiencies and great vulnerabilities in the global food supply chain. You know, we can see with Ukraine right now, global wheat supplies really having problems. So I don't think that there would be a big moral issue if we were to utilize biomass and food to make bioplastics, because we're using what is good in one sector and to make good in another sector, in this case to minimize petroleum plastic pollution. But to minimize any disruption and any stress, we've got to minimize food wastage, and we've also got to make sure that if food is produced, that it's going to where it's needed quickly and efficiently, and not rotting in warehouses or some other similar place.
Okay, I've done a couple of questions which have come up, which are quite similar. One question is, wouldn't it not be better all round to recycle plastic screen protectors that we saw in the skip in your slides? And another one related to that, nowadays a lot of users end up using tempered glass screen protectors instead of plastic ones. So how do you ensure that there is a consumer attitude change towards plastic, bioplastics as a derivative to produce screen protectors? And why would you not just recycle the plastic ones which are there?
So for the plastic screen protectors that are already present in the market, recycling that would be very difficult just for how much one screen protector might last you 1 year. The amount of stress that it goes through for that year will probably make it unusable for any recycling and any future products that could be made for that. So this takes into account that there will be stresses, and afterwards it can be recycled much easier than those plastic counterparts. For the tempered glass,
yeah, and just to add to his point, there's also a great energy requirement when it comes to recycling plastics. It's an energy intensive process, which bioplastics are not as energy intensive. So far as tempered glass is concerned, the main issue is cost, because tempered glass screen protectors are usually more expensive than plastic, certainly more expensive than the bioplastic we made. And this can perhaps preclude people in lower income countries from making it. And then again, we have to look at how this glass is produced, because it's often produced using sand, and this sand has to be silted out from beaches, from other river localities. So I think tempered glass is a valid solution. However, cost and the sourcing of tempered glass raw materials are two concerns that we would have.
Also, adding to Orm's point, our sort of aim was to synthesize a screen protector for a smartwatch, and this particular smartwatch only cost about 20 quid, but tempered glass screen protectors for a phone at least, I don't think there are many examples for smartwatches. They cost about 15 to 10 to 20 quid anyways, so it's not really worth it buying a screen protector which costs almost as much as your watch.
Yeah. And the one question around your alumina that you're using as your support in your material, have you considered the energy intensiveness of aluminium extraction in your bioplastics?
Yes, alumina right now. So it's going to be energy intensive to extract any hardener, because they're used because the compounds, the alternative zinc oxide, titanium oxide, is going to take a lot of energy to extract it regardless of the element. However, our focus was to utilize a hardener that's already in mass production. So alumina is a great ceramic hardener. It's used for transparent ceramics, amongst other things. And so because it's already being made, our reasoning was we wouldn't have to extract much more of it. We could take it out of the existing supply chain. And the amount of alumina included in the bioplastic is not very large. So overall, the energy cost would be bearable. There would still be an energy cost, but it would be bearable.
One last question, and then we'll move on. Have you thought about the packaging of your product? Will that not require lots of plastic as well?
Well, because screen protectors are far more durable than the technology itself, it would be easy just to package it in paper or card packaging. In fact, many smartphones nowadays are coming in just cardboard boxes with no sort of plastic stuffing around them. And they're also excluding sort of other things like chargers from the box. So ideally, we would have it shipped with the smartwatch itself, so that it's all in the same package. But if it's sold separately, then it needs a minimal amount of packaging.
Well, great. I think we're now out of time, so we'll move on to the next team now. Thank you, Falakas, for your presentation. If you could stop sharing your screen so we can then move on to the next team. Thank you, Falakas. So next up is Smart Plastics. So over to you, Smart Plastics. Make sure you unmute yourself, guys.
Can you see our screen and hear us?
We can hear you and see your screen now, yes.
Great, thank you. Hi, we're Team Smart Plastics, and we'll be presenting to you our design and prototypes for a biodegradable lateral flow test. Lateral flow tests are diagnostic devices to test the presence of biomarkers of disease, such as the COVID-19 virus. A sample is added to the testing strip, which contains antibodies to bind to the specific antigens on the pathogen surface. Over the past 2 years, we've been using 1.4 quadrillion non-recyclable, non-biodegradable LFTs in response to the COVID-19 pandemic, which must be thrown away into general waste and eventually into landfills. Plastic is an unsustainable material for a few reasons. One, it's derived from processing oil and gas and coal, releasing harmful pollutants into the atmosphere, contributing to global warming and the climate crisis. Further, it could take 500 years to decompose. During this time, it breaks down into microplastics, which can build up in food chains, threatening the health of animal life, including us. During breakdown, it releases methane and can leak into pollutants into the soil and water. Overall, a terrible carbon footprint. The solution: reduce the product's carbon footprint by making it reusable or recyclable.
You might need to stand closer to the mic. You can't hear you very well.
The solution: reduce the product's carbon footprint by making it reusable, recyclable, or biodegradable. We decided on biodegradable LFTs.
I think your voice is very faint. I'm afraid you'll have to come closer.
For material design reasons, biodegradable materials have shorter lifetime in landfills. By decaying before producing methane or other pollutants, minimizing the environmental impact post-consumption. Thus, locals could experience fewer health complications from water pollution and toxic gas emissions at landfills. Our main objective was to minimize the resistance for consumers to switch to a more environmentally friendly product with low production costs, to evaluate which biodegradable material is best suited to use as an alternative.
I think you need to replace the microphone to be centered on the speaker, because I cannot hear it at the moment. So
yeah,
perhaps just swap places.
Yeah, if we do this, can you hear?
Oh, you want to try and speak now?
Our main objective was to minimize the
No, it's still quite faint.
We can hear the first speaker extremely well, but not the second.
Yeah.
I don't know what to do. I'm really not sure where the mic is. Should we? Let's try doing this. Does that make it easier?
Can you try again?
Our main objective
That's
was
better.
to minimize
That's
the
better.
resistance for consumers to switch to a more environmentally friendly product with low production costs, to evaluate which biodegradable material is best suited for use as an alternative for plastic lateral flow tests. We'll be contributing to the 12th Sustainable Development Goal, which is to ensure sustainable consumption and production patterns. Hence, our main focus is on the second of the 5 Ps, to minimize our negative impact on the planet. During this project, we researched and designed biodegradable lateral flow tests and created prototypes using 2 different primary materials for the LFT cassettes, potato starch and cornstarch. We then carried out biodegradation tests and compared the results to the current plastic lateral flow test manufactured by the Orient Gene Biotech company.
The testing strip in plastic lateral flow tests is made mostly of organic material, such as cellulose and nitrocellulose membranes, except for the glass fiber which reinforces the strip. In our designs, we replaced the glass fiber with PCL or hemp and seaweed. Due to material costs, we weren't able to make a biodegradable prototype of the testing strip.
We carried out a survey with students in our school. 84% of students were willing to use a biodegradable LFT. So we had an indication of that this was a wanted product, and people realized the benefits of switching to a greener alternative.
We created LFT cassette prototypes using 2 primary materials, cornstarch and potato starch. We then redeveloped the prototypes with improvements and then tested their rate of biodegrading. We standardized the sizes and dimensions of the LFTs using a 2-part silicon putty mold.
To create the cornstarch prototype, we added 2 tablespoons of cornstarch.
You might need to move over a bit more towards yourself.
To create the cornstarch prototype, we added 2 tablespoons of cornstarch, which is easily accessible, with 2 tablespoons of water. Then, using a pipette, we added a few drops of vegetable oil. It was then poured into molds, microwaved, and left to dry for about two days. The only challenge faced during the production was after drying. The cornstarch prototype curled up and the 2 parts couldn't be joined to form the cassette. In our developed prototype, we placed a heavy item on top, which made the texture of the bioplastic smooth and allowed it to dry out flat. If we were to continue development, we would find a way to ensure the molds had something to seal the prototype. We also noticed that when we added the buffer solution to the cornstarch prototype, the plastic began to curl after a while as the liquid came into contact with it. To prevent this, we could experiment with the quantities or add another material such as glycerin, which acts as a plasticizer.
To create the potato starch, 4 tablespoons of water, 1 teaspoon of distilled vinegar, and vegetable glycerin, and 1 tablespoon of potato starch were added and then heated. As soon as the mixture began to solidify, it was poured into the molds and they were left to dry for 2 days. The volume of vegetable glycerin had a significant effect on the stiffness of the product. In our developed prototype, we experimented with quantities by adding more than a teaspoon, which caused the prototype to be softer and more flexible, and adding less made it hard and brittle. Suppose we were to continue with the development, we would further experiment with glycerin or use a different plasticizing agent such as soybean oil or triethyl citrate. Further, when it came to the biodegradability test, the potato starch disintegrated sooner than 15 minutes. To prevent this, the starch can be coated in wax and drying oil, composite in a 2:1 ratio to make it waterproof.
One of our criteria was for the LFT to biodegrade after a single use. The cassette should begin disintegrating 15 to 30 minutes after the first application of the sample. It shouldn't begin disintegrating immediately. Otherwise, it could impact the validity of the test results. Method 1 was to dissolve the bioplastic in water at room temperature to replicate the conditions in a consumer using the product. We added 1.9 grams of each bioplastic and plastic as a control and put them each in a beaker filled with water at room temperature. And then we started a stopwatch and observed these after 1 minute and then 10 minutes. Here are our results. Hence, according to the results we collected, cornstarch is the best alternative to plastic when it comes to biodegradability.
We now have some evidence to compare which material is most useful for the lateral flow test cassette. Plastics, as mentioned previously, are derived from fossil fuels whose extraction in itself is polluting.
Potato and cornstarch, however, is sourced from renewable materials, which can be taken from imperfect potatoes and corn separated in supermarkets for aesthetic purposes, reducing food waste at the same time. Our qualitative results from the biodegradability test showed that the cornstarch was the best material to use, as it didn't deteriorate immediately, but began breaking down after 10 minutes for a test strip to produce valid results. The potato starch prototype cost 45p to make, while the cornstarch was made in 22p. Assuming the silicone mold will make at least 100 units, while production costs may vary between companies. Monologic, a manufacturing company, had a production cost of £1.47 per plastic lateral flow. Overall, our production costs are cheaper than plastics, hence consumers won't be impacted by high costs.
Unfortunately, the potato starch was too brittle to be taken out of the case in one piece. Here is the cornstarch prototype, where we used the testing strip from an Orient Genes LFT to demonstrate how it would be used by a consumer or in a clinical setting. It doesn't begin to biodegrade immediately and has dried flat. Obviously, the plastic LFT works well too. To conclude, the biodegradable LFT proved to be a great alternative on a small scale. More specifically, the prototype made out of cornstarch. It was durable and worked well as an actual testing kit, whilst being ecologically friendly.
We noticed that the cost of the production of our casing on a small scale weren't as damaging as they would be on an industrial scale. There's also the risk of economical costs. For example, on the smaller scale that we produced our prototypes on, we noticed that the materials needed weren't expensive due to the conventionality of the cornstarch being an everyday kitchen item. Now, although it's difficult to predict if these costs will be similar on an industrial level, it's overall lower than plastics. If we were to continue developing this project, we would have a larger variety of materials to use for the cassette, such as agar and seaweed, and repeated our testing criteria. Further, we would have attempted to design and make the testing strip to create a complete biodegradable lateral flow test to directly compare with the plastic equivalent.
Our prototypes aren't limited to use in the COVID-19 pandemic. They can be used for pregnancy tests or for existing diseases such as the common cold. Overall, our product has proven to be quite successful in meeting the 12 Sustainable Development Goal. In particular, according to the 5 Ps, we took into account the importance of saving our planet and how our future depends on transforming our approaches to responding to the climate crisis. Through our response to this goal, we believe that our biodegradable lateral flow test could help in reducing waste and increasing sustainability on our planet.
We'll take any questions.
Brilliant. Thank you so much for your presentation. Okay, I'm just looking through the questions coming up. One of the questions, which is still valid for you guys, I mean, we asked the previous team about this as well. So what do you feel that there is any ethical or moral issues around producing bioplastics from food stocks?
So like we mentioned in our presentation, we were planning to use potato and corn from supermarkets which separate their aesthetic and slightly imperfect food waste. So we'd end up using their waste ones, which would lead to less overall use in the plastics, and then we'd be able to use it for our own, rather than taking the ones which are being used in the supermarkets itself. We'd be using the less aesthetic ones.
So another questions which come up on the Q&A, it says in the US, they are using paper covers instead of plastic. Do you think your approach is more sustainable than paper?
Paper covers for the cassette?
I presume so, yes.
The problem with paper is that you're going to end up using trees, and hence that's leading to deforestation. We're using potato and corn as a byproduct of supermarkets wasting themselves. So I think our sourcing is a lot more ecologically friendly.
Yeah. Another question then, how do you think you can mass produce this product while ensuring its quality?
So we can use the mold which we showed in the previous slide, if I can get it up. If we use this mold, we'll be able to get the same size, same dimensions, and that could be used consistently over about, we estimate 100 times before it ends up breaking down. So in terms of making it into industrial level instead of just in a lab, we could use industrial dryers to make it so that it doesn't take 2 days to dry. It takes approximately an hour or 30 minutes, and that will lead to more production.
The other thing is, I mean, the use of the lateral flow test kits are, I mean, we've seen over the last 2 years when the pandemic was at its peak, they were being used on a huge scale. Do you see this product, if this was something that could be viable and implemented, do you see this strategy having a huge commercial interest in the future?
I think so, yeah, because although COVID is...
You might need to move the camera over to you because it doesn't pick up your sound.
Although COVID is coming to an end, there's always
You might need to move the camera more over. It doesn't seem to pick up your voice.
Like mechanism for other things, for example, pregnancy tests or testing for perhaps future epidemics, hopefully not. But yeah.
Okay, good. All right. I think we'll move on to the next team now. Thank you so much for your presentation.
Thank you.
The last team, I will be sharing their video. This is a team which is a year 11 team. They have been sitting their GCSE exams today. So I think they have just joined us now on the call, and they will be here to take the questions, but they recorded their presentation in advance because obviously they didn't want to be distracted with their GCSE exams coming up. So I'm just going to share my screen and put their presentation on, and after we've heard the presentation, we will go to Biogas Renewed to answer any questions. I hope everyone can see my screen now.
Good afternoon, and thank you for having us today. We are Biogas Renewed, and we're ecstatic to present to you our solution to the UN's 7th Sustainable Development Goal, affordable and clean energy for all. For a while now, mankind has come to understand that the burning of fossil fuels is a detriment to our civilization as a whole. The emissions produced are responsible for millions of cases of respiratory issues and deaths worldwide. The use of fossil fuels wreaks havoc on the environment on a scale never seen before in human history, adversely affecting agriculture and destroying the natural habitats of soon-to-be endangered species. In light of the recent spike in oil and gas prices, which has forced countless families into an unfortunate living crisis, we now, more than ever, need to begin the complete phasing out of fossil fuels in favor of more sustainable and less harmful alternatives. Enter hydrogen, a completely clean fuel whose only byproduct is water when consumed by fuel cells. Hydrogen is highly energy dense, storing over 3 times the amount of energy as gasoline by weight. Its low density relative to air allows it to rise and disperse rapidly, a significant safety advantage within an outside environment. Hydrogen-powered vehicles also pose many advantages over their electric counterparts, such as faster refueling times, as well as being much lighter. And so we ask, why haven't we used hydrogen to solve our troubling problems already?
Despite hydrogen's impressive qualities, its unsustainable and expensive methods of production currently make it an unappealing alternative to conventional fossil fuels. Steam reforming, commonly referred to as grey hydrogen, is the most common method of hydrogen production, utilizing hydrocarbons, typically natural gas, as a feedstock. According to the US's Office of Energy Efficiency and Renewable Energy, over 95% of the world's hydrogen is produced by this method, driven mainly due to its low costs and rapid production rates. However, in addition to its use of dwindling finite resources, for every ton of hydrogen that is produced, over 12 tons of carbon dioxide are produced as a byproduct, which is typically expelled into the atmosphere. A more sustainable alternative is the electrolysis of water, also known as green hydrogen, accounting for only 4% of the world's total hydrogen production. It is significantly more expensive than steam reforming, requiring large solar or wind farms to provide the vast amounts of clean energy required to split water molecules apart. Although these facilities produce little to no carbon emissions, their high setup and maintenance costs mean that they can only be afforded by richer, more developed countries, and the increased sustainability often comes at the expense of a hefty price tag typically attached to the hydrogen produced, making cheaper, more harmful fuels more appealing.
Our mission was to develop a new method of hydrogen production that addresses issues such as cost and environmental impact, while putting special focus on deployment within developing countries, whose fragile economies and underdeveloped infrastructure cannot afford to switch to a more sustainable source of energy. Our method relies on cyanobacteria and the enzymes within them in order to produce hydrogen via the biophotolysis of water. Photobioreactors are used to grow cyanobacteria and maintain the required conditions for sustained hydrogen production. This process can be considered cheaper and easier to maintain than current green hydrogen methods, as it relies on plentiful resources such as sunlight, water, and carbon dioxide, as opposed to finite fossil fuels or expensive and unreliable solar and wind farms. Not to mention that it produces no harmful byproducts like grey hydrogen does. Any generated biomass can be harvested and converted into other products such as fertilizer, making the process carbon negative, as it actively takes carbon dioxide out of the atmosphere and converts it into something useful.
Our solution has been designed with portability in mind and hence fits within a 40-foot long high cube shipping container. This enables the use of existing basic transport infrastructure to ship the invention all around the world, providing for both developed and developing countries. The system is highly modular too, allowing for as many or as little containers to be connected at once, providing variable hydrogen production that suits the requirements and limitations of any client. Setting up and deploying it is significantly faster and cheaper than other methods, which require expensive and time-consuming construction projects that lead to widespread destruction of the local environment. Safety also played a key role with the design. Even when critically damaged, any hydrogen leaks will either be too dilute within the photobioreactor's water or will have dispersed into the atmosphere, preventing what otherwise would be a highly dangerous fire hazard. After receiving feedback from a prominent expert in the field, who had also written one of the reference papers that was key to our research, we have determined our maximum theoretical yield to be around 3.68 kilograms, which equates to 41,000 liters of hydrogen per hour of operation.
Moving on to our cost analysis, we have estimated that a single unit will cost around £31,250 to construct and operate. The container will have a lifetime of around 15 years. This means that if we assume a country that uses the solution receives around 3,000 hours of annual sunshine and sells its hydrogen product at a rate of £1 per kilo, it will take just slightly below 3 years for the rig to break even, leaving 12 years to generate a fairly large turnover of £132,480 per unit. Deployment costs are minimal and damage to the environment is negligible. Not to mention that this renewable source of energy will provide local towns and villages within developing countries a sturdy foundation to grow from. Locals can even be trained to become operators of the production rigs, providing new jobs to the populace.
Last but not least, here are our future plans. As we currently only have estimates from other papers and their experiments, our first objective will be to create a small-scale prototype to demonstrate the viability of this project. After we obtain these results, our next goal will be to start optimizing the process and increasing the maximum yield. This can be done through improvements in the photobioreactor's design, ensuring maximum light exposure. Another method would be the genetic modification of cyanobacteria to make it more suited to the purpose of hydrogen production. An example would be the overexpression of hydrogenase, a hydrogen-evolving enzyme. Finally, we plan to expand our research into more efficient ways of storing hydrogen. One potential method would be the conversion of hydrogen into ammonia, which can be stored at significantly higher temperatures than hydrogen itself. In conclusion, we believe that cyanobacteria have the potential to become a source of renewable and cheap hydrogen. With further improvement, our method could finally start to phase out fossil fuels and provide the world a new sustainable foundation to grow from, making everyone's lives a little easier. Thank you.
Okay. I would like to invite Biogas now to turn on their mics and their cameras. Welcome, Biogas. Thank you for joining us. So the floor is now open to questions. I'm just going to have a quick look to see what questions have been posted. One of the questions come up in the Q&A. What parameters were taken into account when calculating the theoretical yield? How realistic is it that this would be achieved in practice? How close could you realistically get?
Okay. So actually, first of all, can you guys hear me?
Yep, we can hear you.
Okay, perfect. So initially we had a really unrealistic value, I think in the range of 18 kilos. And that was because what we did, we simply just took the volume of water that can be stored in each unit and multiplied that by the amount of the density of which bacteria can grow in that volume, and then multiplied it by the production rate of each bacteria, which doesn't really work because in the end, not all the bacteria can be eliminated in the same way, which is why we decided to contact a professor at another university to give us a more in-depth review of what we've done. And we've come to a conclusion that obviously it's going to be much lower simply because the very top layer of bacteria that's exposed directly to the sunlight will be exposed to more light and will then produce the most amount of hydrogen possible. Whereas below that, there will be a slight decrease until the very bottom, around 5 centimeter depth, where 95% of the light will be taken in and then converted into hydrogen. Which is why our new value, we attempted to get a sort of integration between from the top to the bottom to get as much of an accurate value we can. Obviously, it is still a theoretical yield, and I feel the only way we can really test that is to build a prototype to really kind of see what's going on.
Okay, thank you. Another question posted. Would communities need to be trained to handle hydrogen? Additionally, how would communities raise the capital to purchase these?
This is, so two things. So first of all, I feel that, yes, it would either have to be operatives that we hire from other countries to live at these villages and towns to provide the services of operating this thing. They are supposed to be mainly autonomous and self-sufficient. So what we would have to do is just collect the hydrogen and then use it. Obviously, you'd have to provide safety lessons, stuff like that, to make sure that they know what they're doing. However, within long-term use of these products, we can probably teach locals there to operate the machines and provide maintenance, etc. For the second question, what was the second question again?
So it's like, how would they raise the capital to purchase these?
This is where the sort of partnerships would come into play, where ideally at first they would probably have to be purchased for developing countries. But afterwards, once a stable foundation is set up, businesses start to grow, people start to earn more capital, then the governments in the area can actually start to buy more of these units to set up their own massive hydrogen farms to keep the whole system running.
I mean, the other thing is that there's a safety concern with storing hydrogen and ammonia. How do you think you would need to address that?
There are already technologies present just to prevent sort of fires going on with hydrogen and ammonia. So, for example, just keeping them in areas where they are first far away from town or far away enough that if they do cause a problem, they're not going to cause immediate damage to the surrounding towns and villages. Not to mention, as you said before, hydrogen is very light and very undense. Therefore, if there is any leaks, it will simply rise up to the atmosphere, disperse, and not cause a problem. We also, although then again, also you could argue that gasoline, for example, and diesel are also fairly dangerous in storage. If they overheat, natural gas, for example, if it overheats and leaks, it will cause a massive fire. Not to mention that natural gas is more dense than hydrogen and hence would disperse less. So if there is a leak, natural gas would then be more likely to ignite and then cause a massive problem, whereas something like hydrogen would not.
Okay. Another question. What do you think about the demand of your product? Will it be able to replace fossil fuels in a few years? Do you really see that happening? Do you think that there is a bottleneck where consumer behavior needs to be tackled to move from methane to hydrogen?
We believe that regardless of what method, it could be our method, it could be green hydrogen or gray hydrogen, in the end, I feel that because fossil fuels are finite and will eventually run out, and we need to find a way to switch to a more reliable source. So in the end, regardless of what's done, we have to quickly switch to something that can be sustainable so we can keep on using it without worrying about it running out. But at the same time, we just want to make sure that we can make a fuel that is also harmless to the environment. So rather than switching to a sustainable method that still causes harm, we simply can go 2 steps ahead, get a process that is less harmful to the environment as well as sustainable, and it can be used again and again.
Okay, one last question then. I mean, you're looking at producing hydrogen from cyanobacteria, photosynthetic bacteria. I mean, you're going to be working with a particular type of strain. I mean, how durable do you think your cultures are going to be in applying this technology in different parts of the world, where there's very cold and very hot climates?
That's a fair one. We believe that our future projects would revolve mainly around genetic modification, so including pieces of genetic code from bacteria all around the world that have special traits that allow them to survive these environments and implant them into our one. So not only do we make it so it's specialized for hydrogen production, we make it so it's specialized for these random environments and would work better. So that's more of like a long-term project in the future.
That's quite an ambitious project, you know, trying to do genetic modification, making it sound very, very straightforward. Great. Okay. I think we're coming to the end of all the Q&A sessions now. Thank you very much to all the teams for their presentations and participating in the Q&A sessions. We're going to take a short break. It's now on my watch 17 minutes past 4. I suggest we rejoin the call in 10 minutes. So let's say, well, let's round it off. Let's round it off to so at 6:30. So let's rejoin. No, actually 6:30. That should be work. That should work. So let's have a slightly longer than 10-minute break. And in this period, all the judges will get together and we will deliberate on the full presentations. So I will stay on the call. Please don't dial out the Zoom call. Just keep your cameras and your mics on mute, and we will see you shortly at 4:30. Hello, everybody again. Sorry, we were slightly delayed. We had to deliberate for a long time. We felt all the teams did a fantastic job, but we're going to now move on and we're going to continue with the webinar. Next, as part of our program, I'd like to introduce Dame Judith Hackitt, who'll be giving a talk about her career and how chemical engineering has played an important role, hopefully, in her life. So over to you, to Judith. Thank you.
Cameron, thank you. Thank you. Well, hello, everyone. First of all, I just want to say how much I've enjoyed listening to all of your presentations this afternoon, and really, really impressive. I'm not going to tell you the result. That's down to Jane to do after this, but I've just been asked to tell you a little bit about my career, and you're probably thinking, what is this ancient woman coming talking to us? Because I did my degree in chemical engineering in the 1970s, so that's a long, long time ago, and probably feels like even longer to you than it does to me. But I just want to start by reminding you of what it was like back in the time that I chose to do this. So for a girl to want to do chemical engineering was pretty unusual back then. And I have to say that my reasons for choosing to do chemical engineering it was part of a very different plan for me at the time. So what I actually wanted to be when I made the decision to study engineering was to be a teacher. I loved science, I loved maths at school, and I very much wanted to be one of the best science teachers there had ever been. That was my goal, that was my ambition. The reason I chose to go to university and study engineering was because I felt that to be a good science teacher, I needed to be able to help people understand how important science was and how it was applied in the real world. And I felt that I would get a better handle on that by studying engineering rather than pure science, going out into the world and working in industry for a year or two, and then going back into teaching, so I could explain to people and I could answer all the questions then about why is this important? Why do we need to know this? What happened, however, was that plan never came to fruition. I did my chemical engineering degree at Imperial College in London, and then I went out into industry, as was part of the plan, and I joined the biggest oil corporation in the world at the time, Esso, Exxon, as it may be known to some of you. But I worked in the chemicals part of the business, chemicals manufacturing. And once I got out into industry and started working in the chemical sector, I absolutely loved it. I loved the sense of teamwork. I was really, really surprised by how social a profession engineering is. You never do anything on your own in the world of engineering. You always work with other people. And for me, that was fantastic. Bouncing ideas off other people, getting support from other people, tapping into other people's expertise, never having to come up with something on your own. That whole social aspect to being an engineer was really, really rewarding for me when I joined industry and realized just how collaborative it all is. And also when you realize just how much benefit we were delivering for society in the many products that we were producing. I know that may sound now, having worked in petrochemicals, that's a bit difficult to get your head around, given what we now know about the environmental fate of things like plastics and polymers and so on. But at the time, and the value that we felt we were providing in terms of producing those polymers, producing polymers in my case to go into things like tires tubeless tires on cars to make them more energy efficient, whether it be the materials for you putting in engines to improve their lubrication and again to improve their energy efficiency and performance. I could see the reason why we were doing what we were doing and the benefits that society were getting from that. I moved around a little bit in the world of chemicals. I stayed with Exxon for about 15 years. Then I went to work for a very different chemical company producing pigments that were used in many different applications as well. But then after about 20 years in industry, my career took quite a different turn in that I went into the world of representation of the chemical industry to government, trying to speak on behalf of the industry and to work with government on policy around the regulation of industry and chemicals and things like safety in particular. And there's absolutely no doubt that one of the things that came across for me very early in my career in industry was just how important safety and environmental performance are in the role of a chemical engineer. Whatever we do and whatever benefit we deliver for society, it has to be done in a way that doesn't create a safety problem either in the manufacturing process or indeed for those who are going to use our products. So that whole issue of solving one problem and not creating another, either a safety or environmental problem, was writ large for me very, very clearly when I worked in industry. And I took that with me into my role representing the industry and working with government, both at national level here in the UK, and then subsequently in Brussels for the whole of the European chemical industry, which I did for about 2 years. Really getting that whole thing around how do you regulate in such a way that you drive the right behaviors and the responsible behaviors that you need from industry. I did, after about 2 years of doing that, I actually came back to the UK, and my next role was for a period of almost 10 years. I chaired the UK Health and Safety Executive. So this is the regulatory body here in the UK that regulates health and safety in every single workplace in the UK. At the time, a number of people said to me, so you've stopped doing engineering now? Absolutely not. I had not stopped doing engineering. I was still an engineer, still thought like an engineer. And it was very much about getting every industrial sector, from chemicals, of course, and offshore oil and gas, which I'm sure will resonate with Jane, because that was when I first met Jane. We were both working in regulatory fields on opposite sides of the world. So we were very much in the business of developing regulation that helped industry to manage the risks and to deliver those benefits in a way that didn't create risk either for their employees or for society. My career then took, I should also say, I guess, that whilst I was chair of HSE, I was honoured to be asked to be president of the Institution of Chemical Engineers, the role that Jane now holds. And she will tell you more about the Institution of Chemical Engineers later, I'm sure. But it's an organisation that I have very strong ties to and have been proud to be the president of as part of my career. But I guess my career took quite a different turn about 5 years ago, because just about at the time that I was thinking it was time to take it easy, and I'd done my stint in the world of work, a very major incident happened, which I'm sure all of you will remember, 5 years ago when the fire occurred at Grenfell Tower in London. I, like most other people, when I looked at that fire, thought, how on earth did that happen? How on earth can the engineers, not chemical engineers, but engineers who were involved in the design and restoration of that building have practiced what they should be doing in such a way that we created that problem. Because we collectively, I believe, engineers failed to do what we needed to do there. But however, that was my view from the sidelines. It came as a big surprise, therefore, when I was asked by the Secretary of State to actually do a regulatory review and to look at what had gone wrong. Now, I just want to be clear with you, there is a public inquiry still going on into Grenfell, so I'm not going to talk about the details of the Grenfell Tower fire itself and what happened. But what I learned from the review I did of regulation, and what I learned by bringing my skills as an engineer to that, was everything in this world is a system. It is an interactive system. And our ability as chemical engineers in particular to look at the world through that lens of systems that interact with one another, and things that you do in one domain change something somewhere else and have other impacts that you have to think about, really did provide a very different backdrop for me to look at that regulatory regime. I did my review not by reviewing the laws and pointing out with a red pen which laws were wrong and which clauses in the laws were wrong. I did it by drawing a flow diagram of how the regulatory system was supposed to work. In the same way that we as chemical engineers would draw a flow diagram of how a chemical process was supposed to work, I used exactly the same techniques to look at that system. Any of you who have followed the story of what happened following my review, which was published 4 years ago, was that we have now since then been through a process which resulted only 4 weeks ago in all of my recommendations being implemented through an Act of Parliament that received royal assent at the end of April. And we are going to change the way the whole building regulation system in the UK works as a result of that review that I did. Could I have imagined when I was 16 or 17 and decided to become a chemical engineer that one day what I would do would result in an Act of Parliament being passed to change a whole industry? Never in a million years did I think that's what I would end up doing. So by all means have a plan. I did. Be pretty sure you're not going to follow that plan. But having said that, the ability to make a difference in this world is something that I can be absolutely confident that I have done in my career. I was awarded the honour of being made a Dame because of my services to engineering, my services to health and safety, and also for acting as a role model for other women. So I know I have made a difference, and that's what counts. I am proud to be an engineer, and I have absolutely no doubt that if I was making that decision again at the age of 17 today, I would still choose to be an engineer. I think it's highly unlikely that I would go into the oil and gas and petrochemical industry today, but I would certainly want to be part of addressing some of the challenges that our world faces today, which you talked about in your excellent presentations earlier on. So I hope I've given you something to think about. I hope I've given you some sense of how far you can get without having to be pushy about it. It just happens that you have a passion for the subject and for making a difference. And if you like solving problems and tackling big and wicked problems, then engineering is most certainly the profession for you. Thank you.
Thank you, Judith. Thank you so much for that insightful talk. I am dying to ask you some questions, so I'm just going to go ahead and ask some. One of the things that I think a lot of students will be thinking about is, from hearing from you, is, what is it that I would need to do to have a career and have a successful career like yours and be able to end up where you are today. So what would be the key bits of advice you would give to young students which are currently at school?
I think it's to do what you care about. Don't ever follow the herd. So just don't go into a particular part of the industry just because others tell you that's the way to go, or because your friends are going that way. Really examine what matters to you and follow the path in your career that really counts. As I said right from the outset, I was clear why I wanted to be an engineer, but the goal was all associated with my passion to be a teacher. What I actually did as I went through my career was to every so often stop and think about what really matters to me. And as time went on, it became clear to me that this whole issue of doing the right thing and delivering benefits to society whilst at the same time assuring safety in the way we did it, and ensuring that people didn't get harmed, or that the products we produced didn't cause harm to people, became my real passion. So I didn't follow my path by identifying the job I wanted to aim for next. I did it by deciding where my interest and my passions lay and pursuing that.
Another question I wanted to ask was, what were the biggest challenges working with governments? You've had a lot of time where you've been working with different governments on an international level. How would you say, what would you say were the biggest challenges when working in those sorts of environments?
I think short-termism is always a problem when you're dealing with governments. Here we are as engineers trying to find real solutions that will last and which will be sustainable. Governments talk a lot about sustainability, but you have to remember that people who are elected into posts have their eye first and foremost on getting re-elected, and that's invariably only ever 4 or 5 years away at most. So their horizons are very, very different from ours.
Very interesting perspective. Someone's got their hand up, one of the attendees. I presume you're looking to ask a question. My suggestion would be that to put that on the Q&A or on the chat if you have a question. But I'm really thank you for Judith for very insightful talk. I mean, one of the key things you picked up on is be passionate about what you want to do. Yes. And one of my hats in my career is as an admissions tutor at one of the Cambridge colleges. So I oversee all the undergraduate admissions there. And that's one of the key messages we always say to students when they're applying to university, choose a subject you're passionate about, because that's what's going to lead to success. So it's really reassuring to hear that from you as well. So I think we're coming up to 10 to 5 now, close to near the end of the course. So I'm going to now pass on to Jane Cutler to announce the winners.
Okay, thank you, Cameron. Thank you, Judith. It's always somewhat daunting to follow behind Judith's presentation, but as always, she is inspiring and concise and to the point, and certainly always makes me think. So first of all, thank you to our sponsors. Thank you to the students and the schools that put their time and talent into today's event. I understand that over 50 schools and 200 students were involved. So that is a fabulous and quite remarkable number. So already by being on the finalist list today, you're already at the top of a very broad pyramid. So congratulations and well done. We talked a bit in conversation about chemical engineering and IChemE, and as president, I just want to spend a few moments explaining that we're a professional engineering institution. So we're in effect an organisation that's made up of chemical engineers, and we exist to support our members and serve society. We're also led by our members. So I'm president, I'm a member, I'm a fellow, and I sit as one of a board of trustees. And together we steer the institution in the way that we think is best. And we exist to advance chemical engineering's contribution worldwide. So we support the development of chemical and biochemical and process engineering professionals, and hopefully provide network contacts, access to information that perhaps individuals working alone or in smaller groups in the workplace may not have in order to solve the problems that are facing them. Interestingly, we're 100 years old today, so that really does seem ancient even to me. And we've been celebrating or marking the centenary of the profession and the members who've shaped it. So we've gathered together an enormous amount of personal accounts, thought-provoking articles, and a program of webinars where we try and we highlight the importance of impact of chemical engineering in the past, but also try and turn the spotlight into the future and the ideas and solutions being developed for a hopeful future. And one other point about the institution I wanted to highlight is we recognise many of our members actually did their studies a long time ago, and certainly a number of them, sustainability was not a common word, and they were practicing engineers before the UN developed its sustainable development goals, if you can imagine that. So we now have launched in January this year a sustainability hub. And we're going to cover all 17 UN sustainable goals from a chemical engineering perspective. But particularly, and this relates to presentations this morning, there are 4 goals where there's particular relevance for chemical engineers. Number 3, which is good health and well-being. Number 6, clean water and sanitation. 7, affordable and clean energy. And 12, responsible consumption or production consumption. But there'll be knowledge there. But the other really interesting thing is we recognise that being an engineer is not something that you have to sort of leave school, go to university, do a number of years of study, graduate, get a job, and then that's it. It's actually a lifelong journey of learning. So you can actually follow your passion through your career. So we have numbers of modules that are just being developed on sustainability topics. First one's intro to sustainability, as you might expect, and you're probably already well above where that's pitched. But the second one, really interestingly, is ethical. It's about ethics and about ethical decision making, and it throws up some of the challenges very quickly about the importance of systems thinking and the importance of understanding the difference between robbing Peter and paying Paul, about life cycle analysis. And if you're going to use something, understand where it came from and where it's going to go in the future and how we can make it more sustainable. So now to the bit that you're really waiting for, which is the announcement of the winner. And before I did that, I just wanted to talk very briefly about each of the 4 finalists this evening. Sorry, I'm dialing in from Cambridge in Western Australia. So it's about 5 to midnight. So if I get my evenings and afternoons wrong, please excuse me. But what I found really interesting is the goals were really well goal of your project, or the problem statement was really well articulated. Take biogas. What was really interesting about the final presentation and the discussion around that is, I think one of the elephants in the room, and where I am, there are billions of dollars going into, just millions, but billions of dollars going into various hydrogen solutions. But the elephant in the room is, where does all that energy come from? Are we going to take, because ideally you want hydrogen not produced too far away from somewhere where you might put it on a ship and send it somewhere else far away. So that tends to be in places where people live or where people farm and produce food. So it was a really good opportunity to actually call out an elephant in the room and say, hydrogen's great, but current, green, blue, grey, they've all got their pros and cons, and it's not yet a perfect solution. So well done for challenging the current thinking. Secondly, just talking about the smart plastics, and I think this was really a very interesting commentary, because in effect we've all used rat testers, millions of them, as you pointed out, produced around the world, and we've all felt slightly uncomfortable that we're not really grasping, are they sustainable? Yeah, they're good at improving human health, and I can see opportunities to use that type of thinking and that type of testing to move health evaluation from the laboratory and back into the hands of the individuals and empower individuals, but at what cost to the environment. So very impressive for calling out, again, another big problem that is only new, and posing a solution and doing some testing around that. The Philoclose presentation, it's a small thing, but it's a multiplier. But I saw it not just as a relevance to a smartwatch, but a broader concept of, is an opportunity here to provide a more sustainable solution to, if you like, plastics that need high performance characteristics. So that it's asking the question again, is there an opportunity to use plastics, or more sustainable plastics, that can actually just be biodegraded away and produced at a low cost for high performance products? Example used was smartwatches, which are pretty ubiquitous in some areas, but maybe not so much in others. So again, an interesting solution to a problem that many of us probably didn't even know existed. And Izzy Solutions, again, a very clear integration of the different sustainable development goals, not just number 6 about clean drinking water, but its relationship and interconnectivity with a whole load of other goals. The link between lack of clean water and health, and women's education and gender equity, and a whole range of other issues. And the design of their project and presentation was very carefully thought through. Now, you probably don't want to hear me talk for very much more, but what I'd like to do is actually first of all say we have one winner and we have one with a special mention. So I'd like to start with special mention, which is Smart Plastics, for really calling out all of us to say, guys, couldn't you have done a better job? Even if it was just in the packaging, let alone in the rat tests themselves, to actually think more holistically and come up with something where they can be recycled or reused or even turned into road material rather than simply go to landfill. So special mention to Smart Plastics. And finally, like to announce the winner for the 2022 Davidson Inventors Challenge, Team Izzy Solution. So congratulations and well done. And I'd like to award the certificate. So virtual clap. I hope anyone that wants a screenshot has now got one. And then I think I hand over now to the recipients who should be receiving now, or to mute.
Izzy Solutions, can you come online?
Yeah.
Hi.
Do we need to turn off the camera?
Yeah.
Right.
Is the camera come out?
Yeah.
Oh.
Thank you. Someone could probably do a compilation of the photo.
Oh,
So
yes.
congratulations to the winners. And
Congratulations.
special mention to Smart Plastics. So thank you to everyone that participated, and also particularly to your teachers and to all of those in your families and friends that supported it. So congratulations.
Thank you.
Thank you. Thank you.
Thank you.
Thanks, guys. Just to kind of mention what the prize is, I think you're probably wondering what is the prize for the winners. Yes. So the winning team will hopefully we'll be sending you an invitation to Cambridge. You'll be coming and there will be an opportunity for you to stay at Cambridge College overnight and have a tour of the city centre and come and visit the department. We've also, one of our alumni works for Amazon and they will arrange for either a virtual in-person site visit and tour of one of their warehouse facilities, where you can see where all the clever technology that they've put in place to manage all the logistics of transportation of goods around the country. So well done, guys, and I hope you enjoyed the prize. Okay, I think we're coming to the end. Clemens, do you have, I was hoping Dr. Clemens is still here. If you'd like to make any final remarks.
Yes, can you see me and hear me?
Yeah.
I just wanted to say, it was one of my most enjoyable days this week, I must say. I didn't have all enjoyable days, but this was very, very good today. And I was extremely impressed to see the next generation of brilliant scientists coming through. Many, many thanks to Jane and Judith for supporting this event in such a brilliant way. To all of you, you really have achieved something. Out of so many contributions to this event, to come into the top 4 is a real achievement. And I know you've got brilliant careers ahead of you. Do consider a career in chemical engineering and biotechnology, and do consider starting with us. I do invite you to stay in touch, get in touch, have a look, and if you're interested, to make contact. All the best to all of you.
Thank you, Clemens. Thank you everybody again for joining us today, and I think we'll be ending the call here and look forward to hearing from many of you in the near future. Thank you very much, everybody. Bye-bye.